So in this chapter, we're discussing rotational kinematics. So we're back to kinematics, but for the kind of motion where we have rotation rather than translational motion. So I remind you, this is a mechanics course. And as we did before, we studied mechanics first by describing the motion and then by studying the causes of the motion. Namely, we did that with linear motion or straight line motion and then two-dimensional motion. So we're studying mechanics, and now I'm gonna put two new branches, one for translational motion, and now we're gonna talk about rotational motion. In translational motion, the object is changing position as a whole. So if it's at a certain position, it changes its position. In rotational motion, the object can be still in place, but rotating around an axis. So different points of it are moving, but the object itself is not necessarily moving, such as, let's say I have a disk and the disk is rotating around its center. The disk itself is not changing its position. So a good way to say that is I will say the center of mass of the object, which we defined in chapter 9, is changing position in translational motion. In rotational motion, the center of mass can be fixed, but the object itself, points of it are moving around. So different points of this disk are moving around the axis, but the whole disk, if you consider it as a center of mass or if you represent it as a single point, it's not really moving. So we're gonna do the same thing that we did for translational motion, where we talked about kinematics and dynamics. We will do the same here. We will talk about rotational kinematics. And of course, in the next chapter, we will study dynamics, or the forces that can cause motion, and how we can tell if a certain force will cause linear or translational motion, or it's going to cause rotation. So here is our simplest case of rotation. Points on the rigid object move on circular paths around an axis of rotation. So if you look at point A here, it's moving in a circular path around the axis of rotation, which is this vertical line passing through the center of the object. We, of course, can have different motions, different rotations around different axes. So this person here is rotating around this line deliberately. We can have rotations along different axes other than this one. But in all cases, what we have is different points are moving in a circular path. But look at the guy himself, his position as a whole, or the position of his center of mass, is not changing. So here the center of mass is fixed, but points on the object are moving in circular motion. Essentially around a given axis of rotation. So our first most basic approach to study rotational motion and its kinematic, to describe the motion, we will need properties that tell us about the changes in this motion. As we did in translational motion, back then we defined the position, that was our simplest quantity. And then we studied the change in position to be our displacement. And then we studied velocity and acceleration. We're going to be doing exactly the same thing in rotational motion. But one interesting thing in rotational motion, because the object as a whole is fixed, then delta x is 0 here. I cannot talk about change in position. So to describe rotation, I'm going to define the angular position rather than the position X. The angular position theta will be basically the angle that a certain point on the object makes according to a reference, as we did before. For the position X, we define a reference back then we defined the x-axis and the origin and measure with respect to them, and you would choose the origin wherever you want, just measure everything with respect to that. We will do the same thing here for the angle. We define a reference line. Maybe that's where the object starts, and then we start measuring the angle with respect to that line. Of course, just as we did in the x-axis, we defined positive and negative positions according to the origin we chose. Here, I will do the same thing. If we are above the reference line, I'll take this to be positive. If an angle is below the reference line, I'll take this to be negative. Okay, similar to how we measure angles with respect to the x-axis. Things in the fourth quadrant are negative angles. Things in the first quadrant are positive angles. I will write this in a nicer, easier way. Angles counterclockwise from the reference, I'll take them to be positive. So here, the angles I have, theta 0 and theta, I'll take these to be positive angles. And with defining now the angular position theta, I can also define the angular displacement, which is the change in the position. This is delta theta, which is theta minus theta 0. So I can check how much a point rotated. I can say, for example, the point on the disk was here. It moved by an angular displacement of 90 degrees. That's very easy. Then I can immediately deduce that the point is now somewhere here just by moving by 90 degrees or quarter of a circle. So we can see how the angular displacement is actually more convenient. I could, by the way, define the actual displacement of this single point. Like I would say this point moves by an arc distance of 30 centimeters, and then I can just measure how much 30 centimeters are. But the angular displacement is more convenient because if you see that the point moves by 90 degrees, that's easier to visualize than telling you the point moves by 10 centimeters. So same story for the angular displacement. I'm going to take it to be positive if it's counterclockwise and negative if it is clockwise. So if the object is moving in a counterclockwise direction, this object is moving in positive direction. So one thing I can also talk about is the relationship between the angle and the arc distance that an object moves. So if you take this point P here, for example, point P has moved by a displacement theta. So it has moved all the way here and it has covered an angle theta. Now point P has also moved through a certain distance, which is this arc length S. So the actual trajectory that P takes is a circular path. It's not gonna cover the full circle. It's gonna be moving across different arc lengths. So I can relate the angle theta with the arc length by this formula, which you know from math. Theta is equal to the arc length divided by the radius. So theta can be written as S over R. S is the arc length, R is the radius of the circular path. This way we can deduce the angle theta. One thing I want you to be careful about, because S here is in centimeters and R is in centimeters, the units cancel out And then theta is unitless, but I'm usually used to theta being in degrees. So because theta here is unitless, it will be in the angle radian, which you should also be familiar with from math courses. So this angle theta, I will say it is in radian. I can convert it to degrees if I find it more convenient by using the fact that a full revolution is a 360-degree angle, and this is a 2 pi radian angle. And then I can convert from radian to degree. So I will say, let's say the angle was, let's say I got 0.6 rad. Then I can find the angle theta in degrees. It will be 0.6 times 360 over 2 pi. So you can convert from radian back to degree. Of course, the SI unit is going to be radian, by the way. This is more convenient for plugging in different equations. And by the way, for the conversion, you could have also written pi radian to be 180. Then your fraction will look simpler. And here pi, we plug it as pi in the calculator or as 3.14. So let's check an example. Synchronous satellites are put into an orbit whose radius is 4.23 times 10 power 7. If the angular separation of the two satellites is 2 degrees, find the arc length that separates them. So we're given the orbit radius, 4.23 times 10 power 7 meters, and the angular separation between the two satellites is 2 degrees. So I have the angle theta is 2. I will use our formula. Theta is S over R. What we want is the arc length. So we want S. This will be R times theta. R is 4.23 times 10 power 7. Now theta here is in degree, but our formula says theta should be in radian to have unit consistency, right? So here I'm gonna convert from degree to radian. This will be theta in degree times pi over 180. How did I do that? I repeat to you. This angle is in degrees. I know that pi radian is 180 degrees. So 2 degrees will be, this is theta in radian. I make a cross multiplication. We get theta in radian is 2 times pi over 180. So we can calculate S. It should be 1.5 times 10 power 6. What's the unit? Meters. This is an arc length. The SI unit is meters. R was already in meter. And the angle theta, I found it. And that's it. We have another example here on the total eclipse of the sun. The diameter of the sun is about 400 times greater than that of the moon. So this is the diameter of the sun here, and the diameter of the moon. The diameter of the sun is 500 times that of the moon. By coincidence, the sun is also about 400 times further from the earth than is the moon. So I'll name this R. It's also 400, the radius of the moon from Earth. For an observer on the Earth, compare the angle subtended by the moon to the angle subtended by the sun and explain why this result leads to a total solar eclipse. Approximate the arc length to be equal to the diameter of the object. Okay, this is an important comment. We're taking S to be equal to the diameter. So we can deduce that S of the sun is 400 times S of the moon. And we want to find the angle theta. Compare the angle theta theta moon versus theta sun. That's what we want. Compare the angles subtended by each object. So we're obviously going to be using theta equals S over R, where S is the arc length and R is the radius. So here we approximated S to be the diameter itself. This works when you have very large radii, which are much larger than the arc length. So we're given to use this approximation. That's what we're going to be doing. So I write theta of the moon is going to be S moon over R moon. Theta of the sun is going to be S of the sun over S of the moon. S of the sun is going to be 400 S of the moon. So I just substituted what I was given to find the relationship between theta sun and theta moon. I know S of the sun is 400 that of the moon, and R of the moon is also 400 times, sorry, this is sun, R moon. So I just substituted these things, this and this. Now you notice something interesting. 400 and 400 cancel out, and I get S moon over R moon. And this is another but theta moon. I got that theta of the sun equals theta of the moon. What does this mean? If the moon ever aligns with the sun, it will completely block the sun to an observer on Earth. And that's how the solar eclipse occurs. You can take a look here. So the solar eclipse occurs when the moon aligns with the sun and thus blocks all of the light that is coming from the sun. And you see a dark spot because the moon completely stopped in front of the sun and completely blocked the sun because they both have the same angular size. Right? Now, here I want to point out to something that you might think of, which is the solar eclipse sometimes doesn't really block fully the sun. Sometimes we tell you we have partial eclipse occurring. And the sun is not fully blocked. Why is that? Because in reality, the moon doesn't move in a perfect circular path around Earth. It actually moves in an ellipse. So this elliptical path here will be changing its distance to the Earth. So the moon will be changing its distance to Earth as it rotates around it. It's really not moving in a perfect circular path. So the moon distance varies between 356,000 kilometers and 406,000 kilometers. And that will change its apparent size or its angular size. So theta moon will sometimes be larger than theta sun, and the moon can completely cover the sun when they align. The sunlight is blocked, and you have a total solar eclipse. But if the distance is less, if the distance is more actually, theta decreases, the moon looks smaller, it doesn't completely block the sun, and then we have a partial eclipse. So in reality, R is changing, and we know theta is R over D. R is going to be sometimes smaller than the value we studied before, and then theta is going to be smaller. And then the result is we will not really have a perfect solar eclipse. So now, as I did before, we have defined the position rather than the translational position x, we defined the angular position theta, and instead of the displacement, we defined the angular displacement delta theta, the change in the angle. And now next we are going to be studying velocity, and rather than velocity, we will define angular velocity. So how are we going to define the angular velocity? The angular velocity will be none other but the angular displacement over the elapsed time. So before we defined the velocity itself, the translational velocity is what it was delta x over delta t. For the angular velocity, this will be delta theta over delta t. So it's all by analogy, quite straightforward. So we have here the average angular velocity, it will be the angular displacement over the elapsed time. The SI unit of the angular velocity will be radian per second. We can check an example. A gymnast on a high bar swings through 2 revolutions in a time of 1.9 seconds. Find the average angular velocity of the gymnast. So we want W, which is delta theta over delta t. Now here, rather than giving us the actual angle, they told us the gymnast swings 2 revolutions. 2 revolutions means we have 2 full circles. Then I can actually deduce the angle theta, because if we have 2 full circles, this is 2 times the 360, right? Or 2 times 2 pi. I'll keep pi preferably because I want omega, which is in radian per second. So I'll put theta here in radian. 2 revolutions means 2 full circles. So I covered at this at an angular displacement of 2 pi twice, which is 4 pi. The rest is very straightforward. I'll put 4 pi divided by 1.9 and I will calculate omega. As I told you on the calculator, I will put pi be just pi on the calculator, which is 3.14. So you can find here final answer 6.63. And I want you to notice one last thing here. The motion, as shown in the figure, is in this direction, which is clockwise. So we talked before that anything that is clockwise, any displacement which is clockwise, I will, by convention, take it to be negative, just as we did for x. And we said any position x that is to the left of the origin is negative, and anything to the right is positive by convention. Similarly here, clockwise motion is negative, and counterclockwise motion is positive. So because here I have clockwise motion, this is going to be negative, so delta theta is minus really. And this is negative since displacement is clockwise. And thus, my angular velocity, I will also put it to be negative. So we defined the average angular velocity. I can define the instantaneous angular velocity. And as we did before, for the instantaneous translational velocity, this is just d theta by dt. We can find the instantaneous angular velocity of the object. And now we can also move on to define the angular acceleration, which is going to be none other but the change in the angular speed divided by the duration. The unit of the angular acceleration will be radian per second squared. We can check an example. The fan blades are rotating with an angular speed of minus 110 radian per second. As you can see, this is clockwise. The arrow is shown, and the values match that. I have a minus sign. As the plane takes off, the angular velocity of the blades reaches minus 330 radian per second in a time of 14 seconds. Find the angular acceleration, assuming it to be constant. So we want to find the angular acceleration, which we define to be alpha. We said this is delta W over delta T. So this is W final minus W initial over 14. And W final is minus 330. And this is W initial. I can calculate the angular acceleration. You should get minus 16 radian per second squared. So as you can see, I have now defined all of my angular quantities. What I can study next is kinematics for different types of motion. So I will study a constant acceleration motion. We have defined before displacement x, constant acceleration a, velocity v, initial velocity v. So these were for translational motion. And we defined also this was also 1D, this was a straight line motion. And we defined for a constant acceleration these kinematic equations which we use to solve different problems of mechanics. Now we're going to be doing something similar for rotational kinematics with constant angular acceleration. So if I have a constant angular acceleration, I'll simply put the same equations, but I will substitute v by omega, v0 by omega 0, a by alpha, and t here is the only scalar, so it will not really have any change. So I'll still have t. Similarly, I'll substitute v squared by omega squared, v0 squared by omega squared, and a here by alpha, and x by delta theta. So I want you to take a look at our obtained equations. Theta is going to be half alpha t squared plus omega 0 t. I substituted v0 by omega 0. And so this is basically our equivalent of x equals v0t plus half at squared. And our equation here is the equivalent of v squared equals v0 squared plus 2a delta x or d. So the same kinematic equations I just substituted with the new quantities that I defined for rotational motion. So these equations, as before, I'm going to be using them to solve any kinematics problem. You would choose the corresponding or the convenient equation according to what is given to you in the problem. You select the convenient equation among these, and you use it to find the property that you are asked about. So you can see here everything shown in this slide to compare between linear motion and rotational motion. So we have here, rather than x, we are studying the displacement theta. And instead of v, we are studying omega. And instead of a, we are studying alpha, the angular acceleration. And for the equations of motion, x is half at squared plus v0 t. I substitute by omega equals half alpha t squared plus omega 0 t, and so on and so forth. So with this, we make a similar approach to chapter 2 and 3, where we choose our variables, define them, define the positive and negative direction. We write down the quantities that we know, and we select the equation that is suitable according to what is given to us. We select the appropriate equation according to what is given in the problem. So we can take a look at an example, blending with a blender. The blades are whirling with an angular velocity of plus 375 radian per second when the puree button is pushed in a blender. When the blend button is pushed, the blades accelerate and they reach a greater velocity after the blades have already rotated to an angular displacement of 44 radian. The angular acceleration has a constant value of 1740 radian per second squared. Find the final angular velocity of the blades. So what I'm gonna do here is I'm gonna um, I'm gonna just write down what I have. So I'm given the angular velocity when the puree button is pushed, and then I'm given the displacement covered. So this is delta theta. I want you to see how this is given to be positive. Look at the arrow. Yeah, this is counterclockwise. We're also given the angular acceleration. So this is alpha. And what we were given here is none other but the initial speed. When we press the blend button, the blades accelerate and reach a greater angular velocity. So this was their initial angular velocity, and we want the final angular velocity. So what we want is omega. Let's look at our given. We are given omega 0, delta theta, and alpha. And we want to find omega. Let's look at our equations. So I want something where I have omega 0, alpha, and theta. This one is not very convenient because I don't have the time. So rather, I'm going to use this equation. I have omega 0, I have alpha, and I have theta. So I can find omega very easily. So I'll write this down. I'll use omega squared equals omega 0 squared plus 2 alpha theta. So I'll be radical of that. And I'll just substitute everything. Notice how theta is given to me in radian, which is the correct unit. And I found the final angular velocity to be 542 radian per second. So my last section for today is going to be on relating the angular quantities to the limit defined before. So for example, we have defined the angular speed, right? And the angular acceleration and the angular displacement. Now, for the angular displacement, we made a good satisfying equation where we said that theta is s over r. So I can easily find delta theta to be delta s over r, and I will say s is approximately x. So I can find easily a relationship between delta theta and delta x, which is our linear quantity. Similarly, I want to find a relationship between the angular velocity and the actual velocity or the translational velocity of the object. And I want a relationship between the angular acceleration and the linear acceleration of the object. Namely, you can look at this person here who is moving in a rotational motion around a stationary skater. So here we have multiple skaters. They have started next to each other and they are moving in circles around a stationary skater here or a pivot. So one thing I will notice is these all of these skaters are moving together. So their angular displacement is the same. But as you can see, some of them have to cover larger arcs than the rest of them. Namely, the further you are from the stationary skater, the harder the arc that you have to cover. And this means that, translationally speaking, this person is covering a larger distance in the same instant because they're all still moving with each other along the same angular position. So here theta is the same, but translationally speaking, objects further from the axis of rotation will be moving at a larger arc distance. And that makes sense because theta is S over R. If I want theta to be the same for all skaters and S is bigger, actually R is bigger, S will have to be bigger as well. So you can see how if we study the translational aspect of the motion, then we have a different story. We might have same angular speed, but in this figure, for example, the further skater has less or more linear speed. What do you think? Can you give me feedback? All of these skaters are moving together. They have to stay along the same angle. So theta is the same for them all. So theta 1, 2, 3, and 4, the same. But as you can see, S1 is less than S2, less than S3, less than S4. So if you look at the linear or translational aspect, the further skater is moving a larger distance to keep the same angle with the rest of the skaters. Does this mean the further skater is moving at a larger speed or less speed? If he has to cover a larger distance in the same duration, is their speed larger or less? Amir, can you help us?
Yes, Professor. I didn't really get this part.
Yeah. So I'll repeat. These four skaters are moving in circles around the stationary skater here. Now, as they move, they make sure أنه يضلون side by side. All right? Which means that their angular displacement is the same. So the angles are the same. Theta 1, theta 2, theta 3, theta 4, for all three is going to be the same. But as you can see, the skater who is furthest is covering a larger translational distance. Do you agree? And the arc that they cover is larger?
Yes.
So because the distance, the linear distance he is covering is larger, وهن عم يمشوا مع بعض, so the duration is the same. So it's within the same time he has to go over a further distance. And we know that V is equal to D over T. So if the first skater is moving a larger distance within the same time, their speed is gonna be larger or less or the same as the rest of the skaters.
مش
He is
المفروض larger?
covering a larger distance. Yeah, he has to skate faster. So I will say the further skater has more velocity compared to the rest of the skaters because he has to cover a larger distance. Thank you, Amir. And however, comparing the angular quantities, because theta 1, theta 2, theta 3, theta 4 are the same, then omega 1 equals omega 2 equals omega 3 equals omega 4. The angular speeds are the same, but the translational speeds are not. It's good to compare, and it's good to find a relationship between these, by the way. So we want a relationship between theta and r and the speed and the angular speed. Namely, I have this nice relationship here I know that the velocity is the distance over time, which is the distance is this arc. So this is s over time. And s, we said before, theta is s over r. The velocity is distance over time, and the distance here is the arc. So this is the arc over time, which is s over t. But theta is s over r, so s is r theta. I can substitute this here. I'll get r theta over t. Now, theta over t is none other but the angular velocity. I just got that v is equal to r omega. I found a relationship between the linear speed and the angular speed. The translational speed is r times the angular speed. Now, one thing you can notice from here, the larger the radius, the larger the translational speed. That's why the further skater has larger speed. They all have same omega, but his speed was larger because r is larger.